So last class we had looked at how to determine the equivalent circuit parameters of a transformer. So just to reiterate, let me draw the equivalent circuit of a transformer. So we said that we are going to have a single phase voltage, maybe V1, that is being applied to the primary side, and we are looking at R1, we are looking at X1, and we are looking at the no load parameters, which are, let us say, R0 or RC. Generally we call this as RC and we call this as XM. And we are looking at R2 dash, which is the secondary side resistance referred to the primary, and X2 dash, again the secondary side leakage reactance referred to the primary, and we are going to have here the load connected. So let me show the load as ZL dash. So we said that this current, what is flowing through this, is I2. If I look at the secondary current as it is, I2 dash, if I am looking at the secondary current referred to the primary side, and this current is going to be I0. I call this current as the magnetizing current, IM, and this current as the core loss component of current, IC, which is fending for the core losses. And when I add I0 and I2 dash, what I see here is I1. So we drew the phasor diagram also for this. So this is the overall equivalent circuit. We drew the phasor diagram for this. And after that, I told you that there are two performance parameters which we would be talking about. One is efficiency and the other one I called as voltage regulation. These are the major two performance parameters which we would be looking at for any transformer for that matter. Okay. So if we have to talk about efficiency, first of all, we have to say whatever is my output power divided by output power plus losses. And there are mainly two kinds of losses in a transformer. One is iron loss, let me call that as P iron. And the other one is copper loss, which is generally specified as PCU. So these are two different types of losses that we have to account for when we want to calculate efficiency. So efficiency is calculated if I know what is the output power and what are all the iron losses and copper losses. Iron losses I should be able to obtain from no load test. So this is obtained normally from the no load test. And copper losses are basically I square R. They are called copper losses only because they are essentially the dissipation that is taking place within the conductor, right? So that is copper conductor, which is wound around the core. So that is the reason why we call this as copper losses. So I have to write this as I square R. So I square R, if you look at it, generally in short circuit test, we are going to pass rated current through the transformer. But to pass rated current through the transformer, we generally apply very, very small voltage. The voltage that is applied here is going to be really small for the short circuit test. So the flux is going to be minimal. So whatever comes during short circuit test, when the rated current is flowing, I would rather call the short circuit test reading as rated copper losses, because I am passing rated current and the resistance of the winding is intact, right? You are going to have R1 and R2 very much sitting there. So they are going to have the dissipation which are corresponding to rated current. So we call that as rated copper losses. So whatever is the output can be calculated as whatever is the voltage here. If I may call that as V2 dash. So I'm going to have V2 dash, I2 dash, cos phi L, depending upon what is the load power factor. I cannot simply write V2 dash, I2 dash because it's not volt ampere. What I want to see is wattage. So I have to multiply always by the power factor. So I'm going to have V2 dash, I2 dash cos phi L divided by, again, I'm going to have V2 dash, I2 dash cos phi L, which is the output power. And then I'm going to have P iron, because the iron losses are not going to change much. So this iron loss, what you have got here, that is actually what is taking place within the core. So as long as the core has rated flux or rated voltage and rated frequency, generally all the transformers will be operated with rated voltage and rated frequency because it is meant for either stepping up the voltage or stepping down the voltage. Whether I'll draw rated current, that is questionable, but I will always apply rated voltage and rated frequency. Any power system, if you look at it, even if you don't plug in any equipment, the voltage available from your outlet, power outlet, will always be 230 volts, no matter what. The voltage will not change. The frequency will always be 50 hertz. The frequency will not change. So voltage and frequency generally, because they remain as a constant, you are not going to have any variation as far as the flux is concerned. That is the reason why we call generally this iron losses also as constant losses or core losses, because the losses take place in the core. They are constant only because you apply rated voltage and rated frequency. So you are going to apply rated voltage and rated frequency. That is the reason why it is generally going to have constant value as the losses basically. So this will not change, whereas, so I will call this as PC, which is constant or core loss, that's fine. So you can say P iron is also sometimes referred to as P core or P constant. All of them are generally synonymous. Whereas copper losses are going to be I square R. So I2 dash square R. What are the two R values here? If you look at the equivalent circuit, please note that I2 dash and I1 are almost equal to each other. They are going to be almost equal to each other because I0 is a very, very small value. So I1 is approximately equal to I2 dash. So one dissipation takes place in R1, another dissipation takes place in R2 dash. So I may call R1 plus R2 dash as the total resistance, which may be R equivalent. Okay. Similarly, X1 plus X2 dash as the total leakage reactance, which I may call as X equivalent. So I can simply say here that this is I2 dash square R equivalent. That is going to be the copper losses. So this is constant loss, whereas this is going to be copper loss. This is what is the copper loss. So I should be able to write the efficiency basically as V2 dash I2 dash cos phi L divided by V2 dash I2 dash cos phi L plus PC or P iron, whatever, plus I2 square R equivalent. I2 dash square rather, R equivalent. So this is what is efficiency. Now at what point the efficiency is going to be maximum? If I want to know under what value of I2 dash, because I2 dash can change anywhere between 0 ampere to rated ampere. For example, if I say 2.2 kVA, 220 divided by 110 volts transformer. If I take, then I can say the primary current I rated on the primary side is going to be 10 ampere because 2200 divided by 220. That will be 10 ampere. So the current can change anywhere between 0 to 10 ampere, or no load current, which may be very, very small, something like 0.5 ampere or something, to 10 ampere. So I can have variation anywhere. That is the reason why we will not call that the copper losses are a constant. They are not a constant. It depends upon how much is the load current that is being drawn. So I can calculate under what load current efficiency is maximum. So I'm going to say d eta, which is the efficiency, divided by Ti2 dash equal to 0. This is the condition for maximum efficiency. Maximum or minimum efficiency. Minimum efficiency is 0, obviously. So for maximum efficiency here. Okay. So let me try to differentiate this. First of all, let me write eta equal to V2 dash. Let me divide the numerator as well as denominator by I2 dash. So I can say V2 cos phi L divided by V2 dash cos phi L plus P constant divided by I2 dash. I am dividing the numerator as well as denominator by I2 dash. So I'm going to write this as I2 dash multiplied by R equivalent. This is what is efficiency. Now when I differentiate this d eta divided by d I2 dash, I should be able to write only these two are going to get differentiated. Nothing more than that. So this will be P constant divided by I2 dash square with a minus sign because I2 power minus 1. So I2 minus 1 multiplied by I2 power minus 2. So this is what will be the differentiation. And I'm going to have the other one as R equivalent. Nothing else will get differentiated because none of them have the I2 dash term. So this has to be equal to 0. From which I should say P constant equal to I2 square R equivalent. And I2 square R equivalent is equal to P copper. Right? That is copper losses. When the constant losses are equal to copper losses, that is when the efficiency will be maximum for a transformer. Okay. So in general, we are going to say when constant losses or iron losses are equal to copper loss, that is when efficiency is maximum. Okay. Let's understand the statement's meaning. Let's say I have a transformer, the same transformer, let me take 2.2 kVA, 220 volts by 110 volts transformer. Let us say, maybe I am having the constant loss in this particular case to be, let's say, 50 watts. I'm just arbitrarily saying the constant loss is 50 watts, let's say. Okay. And I'm having actually the rated current I rated on the primary side. We said is 10 ampere, right? We call this as 10 ampere because 2200 divided by 220. Okay. If let us say my R equivalent in this case is 1 ohm, that is R1 plus R2 dash, which is R equivalent, that is 1 ohm. I'm just arbitrarily saying again, in which case the copper losses at rated current will be 10 multiplied by 10 multiplied by 1. That is I square R. This is going to be 100 watts. When I am having rated current flowing through my transformer, I am going to have 100 watts as the copper losses. Whereas the constant losses are going to remain constant at this particular value. So if I have to make copper losses equal to constant losses, then the current has to be varied. Resistance cannot vary. Resistance is set in stone. So the current has to come down to how much? I should have this, that is I should say some X square times PCU equal to P constant, where X actually has to be calculated as what is the fraction of current that I will have. So I should say normal copper losses are 100 watts. So I'm going to have 1 by 2 times PCU rated is equal to P constant, which means the current has to be actually 1 by root 2 times I rated, right? That's what it means. Your rated current is 10 ampere. If my transformer is carrying a current of 10 by root 2 ampere, right? In that case, I would have the copper losses also as 50 watts. So the copper losses and constant losses will be equal to each other only at 70% or 1 by root 2 times rated load. That's what it means. So at 1 by root 2 times rated load, at 1 by root 2 times rated kVA or rated current, we are going to have maximum efficiency occurring for the transformer. Okay, so we'll try to do a few problems on no load test, short circuit test, as well as on efficiency calculation in today's class. Any questions on this? Is this clear? So very often you may see that the maximum efficiency of a transformer does not occur at 100% load. It is occurring at, so if I try to plot what is the efficiency versus percentage load on the transformer or percentage I rated. Percentage load I call synonymous with percentage I rated because the voltage is going to be a constant in a transformer. Hardly ever we'll have any variation in the voltage. The voltage will be a constant. Any generating station normally generates only around 15 kilovolts, 12 kilovolts, whatever. That is the rated voltage. Then it will be stepped up to 465 kV or 800 kV before it is actually transmitted. So all those things are set in stone. That cannot change. So the transformer will always be applied with rated voltage and rated frequency. Okay. So if I try to plot how the efficiency is changing, if this is 0 and this is 100% rated current, at 0 there is no output. If there is no output, efficiency is 0, obviously. So it will start from 0, it may peak at some point and then again come down. So where the peak efficiency occurs, at this point you are going to have P copper equal to P iron. Wherever the peak efficiency occurs, that is where the copper losses and iron losses will be equal to each other. Okay. So this is the way normally your transformer graph, the efficiency plot is somewhat like this. And generally the maximum efficiency can be as high as 98 to 99% easily. And even at rated load condition, you may see it very close to 95 or 96%. Generally, transformers are highly efficient. They are not going to be really bad in terms of their efficiency. That is the way they are designed. Okay. Now let us try to do a few So I think the first two problems are from the previous tutorial sheet itself, because we had left out a couple of problems from the last tutorial sheet. So I'm continuing with that. Calculate from the primary side the effective equivalent resistance and leakage reactance of a transformer which gave the following data on test with the secondary terminal short circuited. Applied voltage is 60 volts, current is 100 ampere, power input is 1.2 kilowatt. So this is the gist of whatever is the reading that we got on the short circuit test. So let me take up tutorial sheet 11 and problem 1. So what is given is a short circuit test data which says 60 volts, 1.2 kilowatt and 100 ampere. So this is 100 ampere and 1.2 kilowatt. And also the voltage ratio is not given. It is just saying that primary side, the power is applied from the primary side. That's it. So this is the short circuit test data. If you may recall how we talked about the calculation in the last class. So Z, the impedance, internal impedance of the transformer. Okay, which I may call this as Z equivalent from primary side, that is going to be equal to R1 plus R2 dash plus J multiplied by X1 plus X2 dash, which I can write as R equivalent plus J X equivalent. So this is going to be equal to the voltage divided by the current. So I'm going to have 60 divided by 100. So I'm getting this as 0.6 ohms. So this is essentially your impedance, internal impedance of the transformer. Okay. Now we can say that the power what is dissipated in the resistance will be VI cos phi. And the power is given to be 1200 watts. And this VI cos phi is 60 multiplied by 100 multiplied by cos phi, from which you can get cos phi equal to 1200 divided by 6000. So that is going to be 0.2. The power factor happens to be pretty low in the case of this particular transform. So it is 0.2. So I can say Z cos phi or Z equivalent cos phi is going to be R equivalent, and Z equivalent sin phi is going to be X equivalent. This will be equal to R1 plus R2 dash. It is not possible for us to segregate R1 and R2 dash. Very often what you try to do is R equivalent divided by 2 we'll call as R1. Similarly, R equivalent divided by 2 also we'll call as R2 dash. We assume that both of them should be almost having similar resistance, which may not be the case all the time, but because we don't have a way of separating or segregating these two, we generally happen to do that. So we might say R equivalent divided by 2 equal to R1, which is also equal to R2 dash. Similarly, we would say X equivalent divided by 2 will be equal to X1 as well as X2 dash. This is assumption. Very clearly, we don't have a very clear-cut way of segregating these two. Any questions on this? Is this all right? Okay, fine. So let's look at problem number 2. A 50 Hz single phase transformer has a turns ratio of 6. The resistance and reactances are 0.9 and 1.5 ohm for the high voltage winding and 0.13 and 0.1855 ohm for the low voltage winding respectively. Find the voltage to be applied to the high voltage side to obtain full load current of 200 ampere in the low voltage winding on short circuit. And the second one is power factor on short circuit. So let's try to do this problem. So the problem number 2, turns ratio is 6.9 and 1.5 for the high voltage winding. So let me say N1 by N2 is 6, and I have the values here also rather than repeatedly looking at it. So high voltage side, the values are given to be resistance is 0.9 ohm and reactance is 1.5 ohm. And low voltage side, resistance is 0.13 and reactance is 0.1855 ohm. Okay. So first of all, before everything, let's see whether the question is asking from high voltage side or so. This says that resistances and reactances are so, and the voltage to be applied to the high voltage side. So I want to transfer everything over to the high voltage side. Voltage to be applied to the high voltage side to obtain a full load current of 200 ampere on the low voltage winding on short circuit. So low voltage winding current on short circuit, that has to be 200 ampere. So I can definitely calculate what is the high voltage winding current on short circuit. If the voltage is stepped up, the current will be stepped down. So I should say that will be 200 divided by 6 ampere. Okay. So in which case, I can calculate now, if I want to calculate everything from the high voltage side, please recall what the equivalent circuit of the transformer is under short circuit condition. The parallel branches can be happily neglected, not a problem. And this is short circuited, there is no load. And from here I'm going to apply what is the voltage. So I have to calculate what is R equivalent and X equivalent from the high voltage side, which means let me translate this into high voltage side first. That means this has to be 0.13 multiplied by 6 square, right? If I want to do it to the high voltage side, transfer it to the high voltage side, it will be N1 by N2 whole square. I have to multiply it by always N1 by N2 whole square. So the same way this will also be multiplied by 0.1855 multiplied by 6 square. So I can write this as R equivalent will be equal to 0.9 plus 0.13 multiplied by 6 square. X equivalent is going to be 1.5 plus 0.1855 multiplied by 6 square. Got it? Because this will be R1 and this is R1 and this is R2. So this will be R2 dash now. Similarly, this is X1, this is X2. So this is going to be X1 plus X2 dash. Right? So this is so many ohms and this will also be so many ohms. When you are looking at it from the high voltage point of view. Okay. Now that you have R equivalent and X equivalent, I can simply say R equivalent plus X equivalent, J X equivalent multiplied by 200 divided by 6. That is going to be the voltage V1 to be applied. This is to be applied from the high voltage side. On short circuit. Whenever I am talking about short circuit test, only limiting factor here, which limits the current, is only R equivalent and X equivalent, or Z equivalent on the whole is going to limit the current. Nothing else is there to limit the current. This is the only thing which is preventing the current from shooting up to infinity. Okay, so you should be able to calculate this voltage, right? So please calculate this and check whether it is matching with the answer. What is the power factor on short circuit? So the other one is power factor on short circuit. This will be cosine of tan inverse of X equivalent divided by R equivalent. Right? Okay. So let us try to look at problem 3. I don't know if it is on regulation, then I would like to probably, no, I think this is also equivalent circuit, so it should not be too bad. Calculate the values of R0, X0, RT, XT. Please note, whatever I specified as R equivalent, that is specified as RT here. And similarly, whatever I called as X equivalent, that is given as XT here. Depending upon the book, they may have the notation slightly different. I had called this as RC. These fellows are calling this as R0. I had called this as XM. This is being called here as X0. That's all. So parallel parameters are always determined by no load test, and series parameters are always determined by the short circuit test. So let us try to look at, this is a 200 by 400 volts 4 kVA transformer. So this is a 200 by 400 volts 4 kVA transformer. What is given is open circuit test and short circuit test data. These are given. So open circuit test data is 200 volts, 0.7 ampere, 70 watts. 200 volts, 0.7 ampere, 70 watts. And 15 volts, 10 ampere, 80 watts. 15 volts, 10 ampere, 80 watts. Now what is being asked is, we are being asked to calculate RC, which is specified as R0 here, XM, which is specified as X0 here, and the series parameters, whatever was there in the primary, they have taken everything beyond this parallel parameter. So this is going to be R1 plus R2 dash, which they have called as RT. So let me use the same terminology. So this they have called as RT, and they have called this as XT. Okay, so this is V2 dash and this is V1. So this is the transformer equivalent circuit. Now from open circuit test, you should be able to calculate. So let's do the open circuit test calculation again. So what you have here is 70 watts happens to be P constant or P iron. These are the iron losses. So we will be able to calculate the efficiency of this transformer also very easily, because we have the no load test and short circuit test data. So this is the iron loss. So we should be able to calculate 200 multiplied by 0.7 multiplied by cos phi is equal to 70 watts. Cos phi I should write as cos phi naught because this is no load condition, from which I should be able to calculate what is cos phi naught. Can you tell me what this value is? 70 divided by 0.7 divided by 200. How much is it? Yeah? How much is cos phi naught? This is 0.5, right? Because 70 by 0.7 is 100, 100 by 200 is 0.5. So cos phi naught is 0.5. So directly I should be able to say sin phi naught is 0.866 because this is 60 degrees, right? So I can say I naught cos phi naught will be what is the current through this. If I may call this as IC and if I may call this as IM. So this is IC. So that is 0.35 ampere because 0.7 multiplied by 0.5, that is 0.35 ampere. And I naught sin phi naught will be equal to Im, which is 0.7 multiplied by 0.866. So I think that comes out to be 0.606 ampere. Please check whether the calculations are okay. So once I have IC, I can calculate R naught equal to whatever is the voltage applied divided by IC. And voltage applied was 200 volts. We had 200 volts applied. So I should say 200 divided by 0.35. That is RC. And XM or X naught in this particular case is going to be 200 divided by 0.606 ampere. So you will get these two values as R naught and X naught. R naught I think is 571 ohm and X naught is 330 ohm. Please check the calculations. Okay. So this is the no load test data from which we have calculated the parallel equivalent circuit parameters. Now let us try to calculate what is the series parameters. Which are RT and XT. We need to calculate these two. Okay. Now let's look at the short circuit data, 15 volts, 10 ampere and 80 watt. So 15 volts, 10 ampere and 80 watts. This is the data that is given. So I should say VI cos phi SC equal to 80 watts, which is 15 multiplied by 10 multiplied by cos phi SC. So 80 divided by 150 is going to be cos phi SC. And you can say 15 divided by 10 is going to be Z equivalent, which is 1.5 ohm. This is V by I. That is Z equivalent. Now I can say directly Z equivalent cos phi SC will give me RT and Z equivalent sin phi SC will give me XT. Okay, fine. Maybe this problem we can extend a little bit on our own and we can try to calculate what is the maximum efficiency condition, what is the efficiency at a particular load. Let's try to do that. Okay. So we have got the value R equivalent from the low voltage side, that is 200 volt side is 0.2 ohm and this is 0.3175 ohm. Okay, fine. Let us try to do this further. Let's say at what load efficiency is maximum for this transformer. Let's try to just do that for this particular transformer. Okay. No load test data set 70 watts. So constant losses are 70 watts. And copper losses are 80 watts. Is it rated current? Also we have to say 4 kVA and it said 200 by 400 volts. So, and the current that is flowing on, just a second. I have not taken that into consideration, did I? See, this is on LV side. And this is on HV side. Sorry, I should have told that. This is on HV side. The voltage is applied, 15 volts is applied on the HV side according to the data that is given. This is primary side and this is secondary side. This is on secondary side, that is 400 volts side. So obviously whatever you got as the value, those have to be multiplied by half square. I hope you understand, because 400 volt side we have calculated RT and XT. Okay, so these are on HV side. So if we want it on LV side, this is 0.8 ohm, sorry. That's why I asked you to check the calculation. This is 0.8 ohm. So LV side it will become 0.2 ohm because 0.8 divided by 4. And the same way X equivalent 1.27 ohm comes here when you calculate it as it is, and that is coming out here on LV side as 0.3175 ohm. So this is R equivalent on LV and this is X equivalent on LV. Okay, I have divided it by 4. That's all, nothing else. Any questions? This is essentially 1.27 divided by 4 and 0.8 divided by 4. That's all I had done. Okay. Now, at what load the efficiency is maximum? If it is asked this way, let me first of all calculate 4000 divided by 400, which should be only 10 ampere. But how much is the current that is flowing here? 10 ampere. Fortunately, whatever short circuit data is giving, that is giving the short circuit data at 10 ampere, rated current only. So 80 watts is the rated copper loss. So this happens to be the rated copper loss. When copper loss equal to constant loss, that is when efficiency is maximum. So efficiency is maximum only when copper loss is equal to constant loss. So I want copper loss. So I should say X square times 80 watts will be equal to 70. So X is equal to square root of 7 by 8. So this is the condition under which, this is the fraction of the rated load under which the efficiency will be maximum. Do you understand? Because the copper losses are always proportional to I square. So that is the reason why I am multiplying here by X square. I am multiplying by X square because I want to know the fraction of the load or how much is the current I have to pass through the transformer as compared to rated current. So if I say this is root of 7 by 8, can you tell me how much is the value? 0.76. So that means approximately at 75% load, I'm going to have the maximum efficiency. Okay. So let's calculate the maximum efficiency also. So maximum efficiency at 0.76 times rated load, unity power factor. That also, if the power factor is not unity, you are going to have reduced value of wattage. So let's try to calculate what is the maximum efficiency. So let's say under this condition, first of all, let us try to calculate output. Output will be 4 kVA. So 4 into 10 power 3 multiplied by 0.76. Because if it is 100% load, it will be 1. If it is only 0.76 times rated load, it will be multiplied by 0.76. And unity power factor, which is cos phi. This is the output. So this is 0.935. So this also has to be corrected accordingly. Doesn't matter. So this multiplied by 0.935. That is the output. Now the input is going to be output plus copper losses plus constant losses. Okay. If I am looking at it from the low voltage side, on the whole, I should be able to say the current, low voltage side rated current will be 4000 divided by 200, which is 20 ampere. This will be 20 ampere. Okay. So I'm going to have 20 ampere as the low voltage side current if I'm having full load. If I'm having only 0.935 times full load, I will have 0.935 multiplied by 20, the whole square. This is multiplied by whatever is the R equivalent. What did we calculate as the R equivalent value? R equivalent value on the low voltage side is 0.2 ohm. So I have to multiply this by 0.2. Plus, what is the constant loss? Constant loss is 70 watts. Output I have already calculated here. So this output I have to include here as well. These two will be equal to each other because we have already derived the maximum efficiency condition, which said constant losses will be equal to copper losses at maximum efficiency. So this I can add. So I will have what is the input. How much is the input? Can you tell me? What is the output value first of all? Cos phi is 1. 4000 multiplied by 0.935. How much is 37 watts? Here I want you to, this also should be 70, 70 plus 70. This should be 70. Check it out. So 70 plus 70 multiplied by 70 plus 70, which is 140. 140 plus 0.3740. So this is the total wattage corresponding to, the input. So this will be 3880. So if I try to calculate the efficiency, it is going to be 3740 divided by 3880 multiplied by 100. That is the percentage efficiency. Okay. Let's try one more thing. Let's try to calculate the efficiency at 50% rated load. Let me just do one more calculation, and with that we'll conclude this class. We can continue with rest of the problems in the next class or something. You can also try. Efficiency at 50% load and 0.7 power factor lag. lagging power factor. I'm just arbitrarily taking some value. That's it. Let's first of all try to calculate 50% load. Means the current is 50% of rated current. So, LV side current will be 0.5 times 20, which is going to be 10 ampere. That's it. Okay. And 50% load also means 4 kVA, 4000 multiplied by 0.5 is going to be the VA, which is being output at this point. So that is going to be 2000 VA. So now I can write output is going to be 2000 VA multiplied by cos phi. And cos phi is given to be 0.7. I have simply taken 0.7 as the power factor. So I should say 1400, right? 1400 watts is going to be the output. So this is 0.7. Okay, fine. So this is 1400 watts. If 1400 watts is the output, let me calculate the losses. So losses, first of all, constant loss will not change. That will be 70 watts. Copper loss, originally it said 80 watts multiplied by 0.5 square, where X is the fraction of the load. This is going to be the fraction of the load. Okay, because the current is now half the value. So I square R, when I calculate, it will automatically become X square times whatever is the original value of losses. So 80 watts divided by 4, because this will be 0.25. 0.5 square is 0.25, so I will get 20 watts. The copper losses at this point will be 20 watts. So I can write the efficiency at 50% load, 0.7 power factor lag is going to be 1400 divided by 1400 plus 70 plus 20. So I'm going to have 1400 divided by 1490 watts. How much is this? Huh? 0.9? So 93.9%. Whereas how much was this? The efficiency, maximum efficiency. How much was this? 3740 divided by 3880. It must have been greater. Obviously, it cannot be maximum efficiency otherwise. Huh? 96.39.
So we had looked at the efficiency of a transformer, and we said that the efficiency is generally extremely high for a transformer because there is no rotational loss and there is hardly any leakage. Leakage flux is also very, very minimal. And the magnetizing current, what is being drawn, is also really, really small. So all these things contribute to the better performance of a transformer, and hence the efficiency of the transformer, the resistances of both the windings being small, that makes the efficiency quite high for a transformer. The second performance parameter, what we are going to discuss, that is voltage regulation. So voltage regulation actually refers to how constant the output voltage is. So if the input voltage is a constant, if the input voltage is a constant, are we going to have the output voltage? Or is the output voltage also remaining as a constant, or will it remain uh, as a constant? So this question has to be answered with respect to the performance of the transformer. So if you may recall the equivalent circuit of the transformer, we said that R1 is the primary winding resistance, X1 is the leakage reactance of the primary winding, and we are going to have RC, which is representing the core loss component, and Xm, which is representing the flux that is established in the core, which is linking both the primary and secondary, which is the root cause for transformer operation. And this is R2 dash, which is the resistance of the secondary winding, but it is referred to the primary, which means when I visualize it from the primary, what is the winding resistance of the secondary? And this is X2 dash, which is the leakage reactance of the secondary winding. Now, this is what is going to the load. So we may call this as V2 dash, and this is V1. So if I try to look at the difference between V1 and V2 dash, this is actually the voltage drop within the transformer. This is the voltage drop within the transformer. So, is this drop very less, or it is going to be quite large? So if I assume that I'm applying a 220 volts as the input, and maybe it is a 220 volts slash 110 volts transformer, and let us say it is a 2.2 kVA transformer, which actually is going to cause, if it is in full load condition, we will see normally 10 ampere flowing through this. And if we are translating this 110 also to the primary side, this should also be 220 volts. So will I get the complete 220 volts when I'm applying 220 volts on the primary side and when 10 ampere is flowing through the transformer? If I'm not getting 220, instead I'm getting only 218 volts, then that means 2 volts go as the drop within the transformer itself. So that definitely is telling on the performance of the transformer. The transformer performance is somewhat deteriorated. That's what we would say if the voltage is being dropped within the transformer itself. So we will talk about this voltage regulation in the next class in detail.